Now let's take a step back and look at matrix as a transformation between spaces. That's the way we did when we were talking about Ax equal to b. So if you take a matrix A and then think of Ax equal to b, x is the input and b is the output. X belongs to Rn if the matrix is an m by n matrix, m rows and n columns. So it's a mapping between Rn, taking vectors in Rn and giving you vectors in Rm. It's a mapping from Rn to Rm. It's a transformation between two spaces. So that's the way we looked at it. Now if you take a square matrix, then the input space is Rn, the output space also is Rn. So in principle, if you think of it as an extension of the first statement, that these are actually two different Rns, but then since they are both Rns, we can think of it as the same Rn. So in other words, you can think of A as though it is taking a vector in Rn and transforming it in some way and giving you another vector in the same space. So let me give you some examples though to begin with. If you think of permutation, that is, it takes a vector and it shuffles the elements and gives it back to you. So that we saw, we had permutation matrices. Then we had the projection operator, which also takes a vector in Rn and gives you another vector in Rn, which is actually a member of a subspace, but it's still a vector in Rn. So if you take a three-dimensional vector in Rn and project it to the xy plane, I get a vector, and that vector that I get, the projection that I get, so it's got three components, even though the last component is actually 0. Then there is another class of matrices and operator that does what they call shearing. It returns a vector with one element changed proportional to another element. So we will see an example, then you will understand what I mean by that. So what it will do is to take something like a unit square and then give you a parallelogram that is actually a squashed version of the unit square. So that's why it's called shearing. Then rotation is another example that we saw. It also takes a vector and gives you another vector in the same space but at a different angle, pointing in a different direction without changing the magnitude or the norm of the vector. So these are the different examples. Any matrix that is a square matrix will be a mapping from one space to itself. And I think that mapping is called, if I remember right, automorphism. Now we can ask one question at this point. Are there some vectors that do not change the direction because of the transformation? In other words, I take a vector, all vectors go to some random vectors or some vectors defined by the matrix, but are there some special vectors that stay in the same direction but they just get scaled? So these vectors do not change direction. I put direction in quotation marks because in linear algebra, as it is applied in various fields, vectors may not be vectors with numbers, columns, or things in coordinate space where you can actually think of a direction. So that's the question that we are asking. So let's think about what no change in direction means. That means what you're getting is a scale version of the vector. In other words, suppose you take a vector S and you have a square matrix and you apply the square matrix to the vector S and you get a scale version. Let's call the scaling factor lambda. So you get AS, which is the application of the matrix on the vector S. What you're getting is lambda times S, where lambda is just a member of, it's a real number. It's a member of R. So are there vectors like that? And those vectors are called eigenvectors, and the corresponding value lambda is called the eigenvalue. So that's the definition. So let's look at a few examples before we proceed. Permutation. So if you have a matrix 0, 1, 1, 0, and if you apply it to a vector xy, x and y standing in a column, A, which is, and I want to take AX, this is going to be equal to YX. It just shuffles the elements. So it's a permutation matrix Y that the first element is a 0 times x plus 1 times y, so that is y. The second element is a 1 times x plus 0 times y, that is x. Given that, can you think of a vector that will not change by the application of A? Obviously, if x and y are the same, 1 and 1, then what you're getting is going to be the same because it changes 1, it shuffles x and y, but they are both 1, so you get the same thing back. So that is an eigenvector of this matrix with the eigenvalue 1, because when you multiply, you get the same vector back. Now, if you have 1 and minus 1 on the other hand, when you shuffle these two, you will get minus 1 and 1 because x becomes y and y becomes x. So which is the same as minus 1 times the original vector. So what I'm saying is if I take A times 1 minus 1, what I'll get is a minus 1, 1. But this is the same as minus 1 times 1 minus 1. So this is in the form AS is equal to lambda S. S is this vector or this vector, and lambda is -1. So 2 eigenvectors and 2 eigenvalues. Now if you take projection, if you project to the xy plane, so it's a 3 by 3 matrix, a square matrix still. The matrix, what that matrix does, if I multiply that matrix by x, y, z, it takes x of the first column, y of the second column, z of the third column, but the third column is already 0, so z becomes 0. So I'll get just xy, and any vector xy 0 will not change because it's already on the xy plane, and that will stay the same because I'm projecting onto the xy plane. So that will have an eigenvalue 1. So all vectors on the xy plane will be eigenvectors, the whole of xy plane. Now there is another eigenvector, that is I take any vector along the z-axis, that will become 0, it will become 0, 0, 0, and that is an eigenvector with the eigenvalue 0. So eigenvalues are allowed to be 0, but eigenvectors are not allowed to be 0. Eigenvalues can be 0. So in this case, the second eigenvalue is actually 0. Now, it looks as though we don't have eigenvectors corresponding to lambda equal to 1, but you can take any vector. So typically you would take the basis of the xy plane. The best basis would be 1, 0, 0 and 0, 1, 0, and that would be the eigenvectors corresponding to lambda equal to 1. So the whole xy plane is a space spanned by 2 eigenvectors, so we'll call that actually eigenspace. Now shear matrix, that is interesting. That takes a square and gives you a parallelogram. So an example is there, 1, 0, 0.51, and let me show you what the matrix is. Well, what it does is fairly obvious. A 1, 0, 0.51. So AX is a linear combination of the columns. The first one is a 1, 0, that becomes x0, and I'm adding to that 0.5 times y and 1 times y. So the x component will become x plus 0.5 y, and the y component will become 0 plus y. So the y component stays put, and the x component changes in proportion to y component. So I have, in order to understand what any matrix does to the whole space, you would start with the columns of the identity matrix, the unit vectors, and we'll see what the matrix does to those vectors. So if I take q1 and I say that doesn't change, but q2 becomes 0.5 and 1, that's what the matrix does. The columns of the matrix were 1, 0 and 0.51, but that's what it does. So q1 prime, the transformed q1, is the same as the original q1, but q2 became slanted. So if you think about the unit square there, what happens to that is that it becomes a slanted, sheared kind of a shape. It becomes a parallelogram. That is a shear matrix. That's why it's called a shear matrix. Let's just take 0, 1 and apply the matrix A to it. We know that it changes x in proportion to y, but y is 0 here, so x doesn't change. So x was 1, x is going to stay as 1, and y just stays put. So 1, 0 will stay as 1, 0. I have my A there. I'm going to take S, which was 1, 0. AS is going to be, it is 1 times the first column and 0 times the second column, 1, 0. So lambda is equal to 1, and S, the eigenvector, is just 1, 0. But unfortunately, in this case, we could find only one eigenvector. For a 2 by 2 matrix, we would like to see 2 eigenvectors, but here there is only one, which is important. Keep that in mind. Just to remind you, rotation matrix is an orthogonal matrix, so that the transpose is the same as the inverse, and it's got trigonometric functions inside. Let me just show you why this is true. Again, in order to see what the matrix does, we will see what it does to the unit vectors. So q1 is 1, 0 and q2 is a 0, 1. Those are the columns of the identity matrix. If I'm rotating the unit vectors, the tip of the rotated version will be on that unit circle. If I rotate it by theta counterclockwise, my transformed vector corresponding to q1 becomes cos theta sine theta by the fact that the norm of the red vector, norm of all vectors on the unit circle, is 1, and by basic trigonometry you know that adjacent side is cosine and opposite side is sine, so you get that. Similarly, the blue vector rotating by theta will give you minus sine theta cos theta. So the rotation matrix is actually what it does to the first unit vector, cos theta sine theta, what it does to the second unit vector, minus sine theta cos theta. Now you can ask the question, for non-trivial, by non-trivial I mean if it is a 2 pi rotation, it comes back to the same position, so that doesn't change anything. But non-trivial, something like say pi by 2 or some random angle that is not an integer multiple of 2 pi, you will have a rotation matrix, and all vectors in the plane are going to be rotated. Now, given that all vectors are going to be rotated, there are no vectors that will retain their original orientation or angle. So this matrix does not have any eigenvectors. So all vectors are changed. So there are no eigenvectors, but we will say that no real eigenvectors. We will see why later. The notion of eigenanalysis is not confined to vectors in the coordinate space where you have direction and angles. They are also applicable to vectors that are more abstract, like wave functions or functions. So one such example here for calculus differentiation, if you think of that as a linear operator being applied on a vector which is just a function, this particular function, e to the power ax, if you differentiate it, a just comes out, and what you get, a is just e. So that function as a vector is an eigenvector of this differentiation operator with the eigenvalue which is a. Similarly, if you think of the second derivative of a trigonometric function like sine x, it is just minus sine x, so you get sine x back with an eigenvalue minus 1. So sine x is an eigenvector of a second derivative with an eigenvalue minus 1. So let me define this once more. For a matrix, a square matrix of size n by n, a vector in Rn is called an eigenvector with an eigenvalue lambda, which is a real value. Actually, I should relax this. For now, let's stay with real values. If I can write as is equal to lambda times s for a non-zero vector s, then s is an eigenvector and lambda is a corresponding eigenvalue. Now, one thing to note is that if s is an eigenvector with a particular eigenvalue, any scale version of s, so let's say r times s, is also an eigenvector with the same eigenvalue. If I take a times rs, r just comes out, that becomes r times as, and as we know is lambda s because s is an eigenvector. So it becomes lambda times rs. So if you think of rs as another vector, that also is an eigenvector of a with the same eigenvalue. That basically means eigenvectors define only directions. We're not really interested in the magnitude. So for that reason, we will typically just normalize the eigenvector. So if you do it in Sage Math, I believe you will always get the normalized version of the eigenvector. Now another thing is that lambda can be 0, as we saw in the projection matrix projecting to the xy plane. And if it happens to be 0, what it's saying is that a times s is the 0 vector, which means s is a member of the null space of that matrix. So any matrix that has a null space will have a bunch of eigenvectors in the null space. But s is never a 0 vector, much like for the null space also we're looking for non-trivial vectors that are in the solution set. So here I'm relaxing the statement that for a real matrix in R n by n, the eigenvectors and eigenvalues may be complex. Let's take a look at how to compute eigenvalues.